Now, the next question is example 1.11. Okay, here they gave the set S consists of the elements 1, 2, 3, and the relation instead of the notation or, here they mentioned another notation. It is called as row. Oh, so notation only they changed it, but even there's a relation only. Okay, this is one relation, row. Okay, all right. What are the pairs here? 1, 1, 1, 2, 2, 2, 1, 3, 3, 1. These are the pairs given in the relation row. Now we should verify this relation is reflexive, symmetric, transitive, or else an equivalence relation. If it is not, what are the pairs needed to be included here to make it is reflexive, symmetric, transitive, and equivalence relation? First case, for reflexive, okay, S consists of the elements, 3 elements, 1, 2, 3. Then in the relation 1, 1, 2, 2, 3, 3 should be there. Then only it is reflexive. Here 1, 1, okay, 2, 2 is ready. But which is not here, 3, 3 is not here. It is not reflexive. Include the pair. Include the pair 3, 3 for reflexive. Okay, if you include this pair, then it becomes a reflexive. Second case, symmetric. So symmetric means we can leave about the same elements pair. These 2 pairs we can remove. Okay, then we can verify for the remaining 3 pairs. 1, 3 is here. Then what is the reverse order? 3, 1. So this pair is satisfied about symmetry. This pair 3, 1 is here. That is the reverse order 1, 3. So these 2 pairs are satisfied about the symmetric property. Then you should verify for this one. 1, 2 is here. What about 2, 1? That is not presented here. Then this is not symmetric. Okay, it is not symmetry. Include the pair. Include the pair 2, 1 for symmetry. Okay, if you include this pair, then it comes as a symmetric relation. Then third one, for transitive, we can leave about the same element pair. These 2 pairs we can remove. For this pair 1, 2. Okay, now this is first pair. Then we should verify with some other pair. In that 2 will be the first element. This is the like that element. So 1, 2, 2, 2, then 1, 2. 1, 2 is presented here itself. So this element satisfied about transitive. You can leave this. Now come to here. 1, 3, 3, 1, then 1, 1. It is here. So it is satisfied. Take this pair 3, 1. Okay, so 3, 1 means here 1, 2, 3 pairs are there. Started with 1. Okay, 3, 1, 1, 1. Then it is 3, 1. It is here. No problem. 3, 1, 1, 2. The pair 3, 2 does not given here. Like as 3, 1, 1, 3. The pair 3, 3. That is also not here. So we need 2 pairs to make it is transitive. Okay. So it is not transitive. It is not transitive. Include the pairs. Include the pairs 3, 2. 3, 3 for transitive. Right. Up to we verified about transitive. Now we can verify about equivalence. It is not an equivalence relation. It is not an equivalence relation. Then what are the pairs needed to include here means, if you include this pair, it will come as reflexive. If you include this one, it will come as symmetry. And the same element 3, 3 is presented here too. Then we can take this one. Okay, include the pairs 3, 3, 2, 1, and these two are here, but 3, 3 is already repeated here. Then we can take this case only. 3, 2. Now see, if we include these 3 pairs, then it will not come as an equivalence relation. Because, see clearly, if you include this, it will be reflexive, satisfied, okay. 2, 1. If you include 2, 1 here, you can leave about these 2 pairs. 1, 2, the reverse order. 2, 1 is included, right? Okay. Then 1, 3, the reverse order. 3, 1 is included, okay, right? Okay. Then we come right. If we add these 2 pairs, so 3, 3 is already leave it. 3, 2. If you include this one, it will come as transitive, right? Okay. If 3, 2 is here, then what is the symmetric order 2, 3? That is not should be there. Okay. Then we should add that 2. If we include 3, 2, then we should additionally include 2, 3 to make it is equivalence relation. Okay. Include the pairs. Include the pairs 3, 3, 2, 1, 3, 2, and addition. This is additional one. Okay. For equivalence. Relation. So finally, the relation R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 3, 1, 1, 2, 3, 4, 5 elements are there. Additionally, we should include these 4 elements. 1, 2, 3, 4, 5, 6, 7. Remaining these 3. 2, 1, 3, 2, 2, 3. Now this relation will satisfy all the 3 relations. Reflexive, symmetric, transitive. Okay, then it is an equivalence relation also. Now we are going to discuss about the remaining questions in the exercise 1.2. Question number 3. In this question, they gave one set. Set A is equal to set of all elements A, B, C. It consists of 3 elements. And relation R from the set A to the set A. That we can read as relation on A. The relation R on A. A in the sense means from the set A to the set, both are the same here. Okay. And the relation is given as A, B, B, and A, C. They gave only 3 pairs. They gave only 3 pairs. Now, what are the pairs to be included here to make it is reflexive, symmetric, transitive, and an equivalence relation? For these 4 relations, what are the pairs needed to include here? First case, for reflexive, A contains 3 elements. A, B, C. A contains 3 elements A, B, C. Then surely for reflection the pair C, C should be here in this relation R, but that is missed here. Then we should include that. Okay. Include the pair. Include the pair C, C for reflexive. So if we include the pair in this relation, then it is automatically come as reflexive. Second one, for symmetric, actually I told in the previous class, same elements pair, A, B, B, C, C, like that means surely it will satisfy reflexive, symmetric, transitive. So we should check once for the different pairs only. Here we can leave about the same element pair. See this pair only. If A, C belongs to R, so here A, C belongs to R only. If you want to say this is symmetric means surely the pair C, A should be in the relation R, but that is missed here. So include the pair C comma A to make it is symmetry. Include the pair C comma A for symmetry. Third case. Anyone can tell me, is this transitive or not means? It is transitive only. How it means? What is the condition for transitive? We can leave about the same element pair. We can leave about the same element pair. And see this one. The condition for transitive A comma B and B comma C, if both are included in the relation, then we can verify about A comma C belongs to the relation or not. But here A comma C only is presented. There is no another pair which is started as the first element with C. There is no other pair which is started with the first element C. Then how do you verify AB, BC, then AC belongs to R? That is not possible here. So here by the given relation itself already it is transitive only. So here you don't need to add any other pair. Already it is transitive only. Already it is transitive. So no pairs needed here. Okay. No pairs needed. Okay, then for an equivalence relation, it satisfies reflexive, symmetric, transitive. Here, transitive is satisfied, right? Then we should verify these two cases. We should verify these two cases. So include this pair for reflexive and this pair for symmetric. So include the pairs CC and CA for equivalence. Include the pair CC and CA for equivalence relation. That's all. Okay. And one more thing. This sum is same as the question number 2. Question number 2. So what is the difference between the question number 2 and question number 3 mean? Here the element D is not given. But in question number 2 they gave 4 elements A, B, C, D. That only one pair we reduce it in this case. That's all. Both are the same type of questions. Now the next question is question number 5. Okay. Here the relation R is declared on the natural number set. And the relation, how they defined means set of all pairs A comma B which satisfies the condition 2A plus 3B is equal to 30. In that A and B are belongs to the sets natural numbers. Okay. So how it means? From the natural numbers, what are the two numbers which are satisfying this condition? 2A plus 3B is equal to 0. The two numbers only having the pair. The relation R. Okay. Now we should verify what are the pairs are there. Now listen. Take 2A plus 3B is equal to 30. In this 3B is equal to 30 minus 2A. 30 minus 2A. Then B is equal to 30 minus 2A divided by 3. So here we can substitute the value for A and we can get the value for B. But both should be the natural numbers. So natural numbers means starts from 1, 2, 3, 4, 5 up to etc. infinity. 0 is not included here. Okay, so you cannot apply about 0 here. Then start with 1. If A is equal to 1, then it will be 28 by 3. B will come as a rational number. That's not possible. A is equal to 2. Then 4. 30 minus 4, 26 by 3. Again is a rational number. 3. 3 into 2, 6. 30 minus 6, 24. 25 by 3 means then B is equal to 8. Now both are the natural numbers. Like that we should verify one by one. So if A is equal to 3, which implies B is equal to 8. This is one pair. like that. So once A is exist means here the division is also 3. Surely the answers will come as multiples of 3 only. Okay. So directly you can go to the value A is equal to 6. But I am verifying step by step. If substitute A is equal to 4, 8 will be here. 30 minus 8, 22. 22 by 3 is not a natural number, rational number. A is equal to 5, 10. 2 into 5, 10 now. 30 minus 10, 20. 20 by 3 again is rational number. Substitute about 6. 2 into 6, 12. 30 minus 12, 18 will be there. 18 by 3 is 6 now. So if A is equal to 6, then B is equal to 30 minus 12 means 18. 18 by 3, then it is 6. Okay. Then like as A is equal to 9, 18 will be here. 30 minus 18, 12 will be there. Then B is equal to, here increasing by 3, 3, 3. Here decreasing by 2, 2, 2. Okay. A is equal to 12. A is equal to 12. 2 into 12, 24. 30 minus 24. Then it will be 6. 6 by 3 means B is equal to 2. So, or having the pairs. The relation or having the pairs 3, 8 and 6, 6, 9, 4, 12, 2. So now only we got the relation. Okay. Here they gave with one condition. We should form the proper numbers to verify they are reflexive, symmetric, transitive, equivalence. This relation only we needed now. Okay. Now the first case, is this reflexive or not means surely this is not reflexive because it's a natural numbers. Okay. So if 3 means 3 exists in one pair, 3, 8 is here, then surely 3, 3 should be there and 8, 8 also should be there. So 3, 3 is not here. 8, 8 is not here, 9, 9 is not here, 4, 4 is not here, 12, 12 is not here, 2, 2 is not. 6 pairs are not existed here. But this is enough case to say about only one case. Okay, now I am going to say about 3, 3 does not exist in the relation. So it is not reflexive. Okay, 3, 3 is does not belongs to R. So reflexive is not true. Reflexive is not true. Second case, symmetry. So 3, 8 is here. Then the reverse pair 8, 3 does not exist here. Like as for 9, 4, 4, 9 is not here. 12, 2, 2, 12 is not here. So one case is enough to say it is not symmetric. I am going to say only one case. Here 3, 8 belongs to R, but 8, 3 does not belongs to R. Therefore, symmetry is not true. Third case, is this transitive in the sense means it is transitive only. How it means? You can leave about the same element pair. Remaining 3 pairs only we can check. For this pair 3, 8, then there should be some other pairs. In that 8 will be the first element. So like their pairs are not here. So for this pair it is satisfies about transitive. It is transitive only. You can leave this. Come to this pair. 9, 4 here. 9, 4. Then there should be one more pair which is started from 4 as the first element. Like their pairs are not here. Then this is also transitive. Like for this one, 2, something means like their pairs are not here. Then this is also transitive. Transitive is true. Transitive is true. Since A, B, B, C does not belongs to R. This is the reason why we are saying this is transitive. Okay. Fourth one, for an equivalence relation. This is not an equivalence relation. It is not an equivalence relation. What is the reason? Actually, for equivalence relation, all these three properties should be satisfied. Here reflex is not true, symmetry is not true, transitive only true. Therefore, it is not an equivalence relation. Next question, question number 9. Here, the relation R is defined on the integer set. So, on the integer set means from the set to the set, both are integers. Okay. And the relation, we mentioned about M or N. M relation with N. That we can write as an ordered pair, like as M comma N. Okay, what is the relation means? The value M minus N is divisible by 7. Divisible by 7 in the sense means, while dividing this value by 7, the remainder should be 0. When the remainder should be 0, if the value M minus N is a multiples of 7, then only by dividing 7, we can get the remainder as 0. By using this relation, we want to verify either it is an equivalence relation or not. So, equivalence relations mean we should verify all the three properties. Reflexive, symmetric, transitive. All the three we should verify now. First case, verify the pair M comma M. That is M minus N. By the relation, I am coming to the proof. Okay, M minus M is equal to 0. Then it is 7 into 0. We can write. This is nothing but multiple of 7. So if it is multiple of 7, it is divisible by 7 also. M minus M is divisible by 7. So this implies the pair M comma M belongs to R. Therefore, reflexive is true. Reflexive is true. Second case, symmetric. Okay. So for symmetric, if M comma N exists in the relation R, then only we can go for the relation M comma M. Okay. Then first we should verify about M comma N. If M comma N is belongs to R, this implies M minus N is divisible by 7, is divisible by 7. So when it is divisible by 7, if it is multiples of 7 only, it is divisible by 7. Now multiply with one minus, then it will come as N minus M is equal to minus 7k, then it is 7 into minus k. This is. Now this is also multiples of 7 only, then it is also divisible by 7 also. Then M minus M, N minus M is divisible by 7. Therefore, this implies the pair N comma M is also belongs to R. The pair N comma M is also belongs to R. Therefore, symmetric is true. Symmetric is true. Third case. Now, third case, if M comma N belongs to R and N comma P is belongs to R. So this implies M minus N is equal to 7 times K. That is multiples of, divisible by 7 is multiples of 7. And the pair N comma P is also belongs to R means N minus P is also multiples of 7. Now add these two values. M minus N plus N minus P is equal to 7K plus 7L. N and N we can remove. This implies M minus P is equal to 7 into K plus L. Let us assume the value K plus L as another scalar lambda. M minus P is equal to 7 times lambda. This is also multiples of 7 only. Then this is also divisible by 7. Which implies M minus P is divisible by 7. this implies m comma p is also belongs to R. Now see here, m comma n belongs to R, n comma p belongs to R. Now the value n and p we can remove. Remaining it is m comma p. That is also belongs to R. Therefore, transitive is true. Transitive is true. Now all the relations, three relations are satisfied. Therefore, it is an equivalence relation. It is an equivalence relation. Actually, this sum is nothing but the same model of example 1.13. That example 1.13 they gave is a divisible by 12. Here it is divisible by 7. Instead of 7, there we use it about 12. That's all. Both are the same method questions. Now, we are going to see one notes. Okay, in that only one point is there. For an empty relation, empty relation means a relation in that no ordered pairs should be there, no more contents. Actually, empty relation, this is like this only. A relation which consists of no pairs. Okay. How it is satisfies about the symmetric, reflexive, transitive means it is not reflexive. Second one, it is always symmetry. Third one, it is always transitive. That means empty relation is not reflexive but it is symmetric and transitive. Symmetric and transitive. This one result. Okay, this we are going to use in the exercise sum. Now, in the exercise 1.2, the first question. Okay, in that relation R is declared on the set positive integers. Actually, Z means integer set. Z power plus means positive integer. Relation on the set is Z. On the set means from the set to the set both are the same. Now both are the positive integers. And what's the relation here? M comma n, the pair. It satisfies m divides n. M divides n. This is nothing but n by m. M divides. M will divide the value n. The remainder should be 0. The remainder should be 0. Right. This is the condition here. This is a relation. Under this relation, we are going to verify what are the properties it is satisfying. First one. A number always divides the number itself. It is possible only. Okay. M divides m. This is possible always. Okay. So this implies the pair m comma n belongs to R for every m belongs to the positive integers. Okay. Therefore, reflexive is true. Reflexive is true. Second case, symmetric. Symmetric means suppose if m comma n belongs to R, this implies m divides n, but n sometimes n divides m is possible and n divides m is not possible, but n divides m is not true. How it means? I will give one example. M divides m means n should be in the numerator, m should be in the denominator. Now we can say 2 divides 4. 2 divides 4. That is possible. 4 by 2. Answer is a positive integer. That is important. Here the relation is declared on the set positive integer, the answer should be a positive integer. Here if you cancel these two, we get plus 2 is a positive integer. But the converse, 4 divides 2 means it is nothing but 2 by 4. Now the answer is an fraction 1 by 2 is a rational number. Okay. So now this answer does not belong to the set z power plus. It is not possible. So symmetry is not satisfied. Okay. But n divides m is not true. This implies symmetry. Symmetric is not true. Okay, then see the third one. If m comma n belongs to R and n comma p is belongs to R, this implies m divides n and n divides p. Now m divides n and n divides p. If m divides n means this value, answer should be a positive integer. Do the cross multiplication, then n is equal to k into m. So like as if n divides p, here take some other constant, then it is p is equal to n into l. So here we can write n is equal to k into m and p is equal to n into l. Okay. So now take this part, value p. P is equal to n into l. Now we can replace the value n as like as k into m into l. Now we can take m as outside and remaining it is l into k. That value l into k we are going to take as lambda. Now this is m into lambda, this is p. Do the cross multiplication, then it is p by m is equal to lambda. What is meaning in this? Then m divides p. M divides p. This implies m divides p. Therefore, this implies the pair m comma p will exist in this relation R. Therefore, it is transitive. Transitive is true. So here, reflexive is true. Symmetric is not true. Transitive is true. So it is not an equivalence relation. Now the next question is second subdivision. First question, second subdivision. Here the set is set of all straight lines. So all type of straight lines are there. Okay. Here the relation R is declared as from the set P to the set P. Two lines L comma M. And the condition is L is perpendicular to M. So like this. If suppose they are taking two lines, here L is one line and M is another line. If these two lines are perpendicular, then the pair L comma M belongs to this relation R. Suppose if you are taking L and M like this means it is not possible because here they are parallel. Parallel lines are not in this relation. Which two lines are satisfied the perpendicular case? That lines will be taken in a pair in the relation R. Okay. So here we are going to verify about the three relation by this condition which is given. First one, reflexive. Every line is perpendicular to the line itself. Is that possible? It is not possible always. Okay. Every line is parallel to the line itself. That is possible. It's not possible to get the perpendicular to itself. So reflexive is not possible here. Every line is not perpendicular to itself. So therefore reflexive is not true. Okay, then The second case now, if L comma M belongs to R, this implies L is perpendicular to M. The line L is perpendicular to the line M by this diagram. This is one line L, this is another line M. Now these two lines are perpendicular. If L is perpendicular to M, what is the reverse case? M is also perpendicular to L only. That we can say. M is perpendicular to L. This implies the pair M comma L is belongs to R. Therefore, symmetry is true. Transitive, if L comma M is belongs to R and M comma N is belongs to R. So how can we represent the diagram means, this is line L, this is line M, now these two are perpendicular. Okay, and one more pair M comma N, this is another line N, these two are perpendicular now. Now see clearly, if these two are exist in the relation R means, clearly we can get L is perpendicular to M and M is perpendicular to N. But for the transitive case, we should get L is perpendicular to N. L is perpendicular to N. Then only the transitive is true. But here, L is perpendicular to M. That is okay. M is perpendicular to N. That is also okay. But what about L and N? They are parallel to each other. But L is parallel to N. So this implies L is not perpendicular to N. Therefore, the pair L comma N is does not belongs to R. This implies transitive is not true. Transitive is not true. That's all. Now, the fifth case. Here the relation R is declared on the natural number set. Natural number means 1, 2, 3, 4, 5, 6, up to etc. infinity. And the relation is declared as x comma y. What is the condition here? X plus 2y is equal to 1, where x and y belongs to the natural number set. So what are the numbers? From the natural numbers, those who are satisfying this condition, the pairs we can exist in the relation R. Okay. So but we should verify what are the numbers will satisfy this condition. Okay. Take x plus 2y is equal to 1. From this, 2y is equal to 1 minus x. Then y is equal to 1 minus x by 2. Here, x and y both are the natural numbers. Then we are verifying what are the natural numbers satisfying this condition. We can start from 1. If x is equal to 1, then y is equal to 0. It's not possible. Both should be natural number. That is the condition here. Here x is a natural number, but y is not a natural number. It's a whole number. It's not satisfied. Suppose x is equal to 2, then y is equal to minus 1 by 2. Then x is equal to 3, then y is equal to minus 2 by 2, that is minus 1 now. So this is not possible. This is not possible. When x is equal to 4 means, then y is equal to minus 3 by 2. That is not possible. So we cannot get a proper pair to satisfy this condition by the elements which are taken from the natural number set. So that is not possible here. So here the relation R is an empty relation only. The relation R is an empty relation because all these 4 pairs are not possible. Not only these 4 pairs, remaining whatever value we can substitute, this will come as negative here because if it is 1 means the numerator will come as 0. Suppose the value of x is more than 1 means then the numerator will come as a negative 1. Then we can get the value as a negative value. Sometimes it may be negative integers, sometimes a negative rational numbers. But whatever it is, the value of y is not a natural number now. Okay, so you cannot get the proper pair. So here I did some sample values only. That's all. Here the relation R is an empty relation. But I gave you one notes. Okay, in that an empty relation always not reflexive, but it is symmetric and transitive. By the property, an empty relation always not reflexive, but symmetric and transitive. Symmetric and transitive are true. Reflexive only failure. Okay.